In a previous video, we gave an introduction to principal component analysis, and we saw that when you have a matrix of observations like this matrix A, you can calculate, after removing the mean from each row, the mean of each row from each row, you can form the sample covariance matrix. This is the sample covariance matrix, S. And that's a symmetric matrix, and by the spectral theorem, it can be written in the form Q lambda Q inverse. And the columns of Q, those are eigenvectors, and those unit length eigenvectors are called the principal components of A. And since Q is an orthogonal matrix, these form a 90-degree angle with each other. And we've seen that the first principal component is the direction that captures the greatest variance in the data. That's a sort of vague, intuitive way of thinking about the first principal component. And we've shown that because the variance in that direction is the value of a quadratic form. Where is it? It's somewhere. The sample variance is, yes, it's here. This is the variance of the linear combination Cu plus dV, where U and V are the rows of B. So you get this quadratic form, and then we apply the facts about quadratic forms to figure out how to interpret the principal components. But there's another interpretation of the principal components, and that's what I want to talk about in this video. And this time we're going to work with the columns of our matrix. So again, so we have another interpretation of principal components. And let's take the same example that we had before, the same matrix A, and recall that when you take the mean of each row and then subtract each row's mean from the corresponding row, you get this matrix B, which was this. And we looked at the sample covariance matrix, which was this, right? This was the sample covariance matrix. Now let's say that I have a unit vector, U, and I evaluate U transpose SU. So remember, that's the variance in the direction U if U is a unit length vector. So this is the same as 1 over n minus 1 times, okay, let's say that U has components x1, x2. And let's work with the columns of B. So let's say that the columns of B were B1 all the way to B6. So I have B, okay, it's this matrix, and then I have this matrix times the transpose. right? Now let's take a look at what this is. This is a row vector, and the entries in each row are, so this is my vector u. The first entry is u dot b1. And since dot product is commutative, I can write that as b1 dot u. And then the second component is b2 dot u. And then it goes out to b6 dot u. Right? And then I have the transpose of that, so that's b1 dot u all the way to b6 dot u, just written as a column, and then I have this 1 over n minus 1. And so this quantity is equal to this, and then that's equal to 1 over n minus 1 times b1 dot u squared plus b2 dot u squared all the way to b6 dot u squared. Okay. Now remember, u was a unit vector. So do you remember how we can interpret b1 dot u? It can be interpreted in terms of the projections, because the projection of b on u is b dot u u. So this b1 dot u is the coefficient of u in the projection. So when I square that, I just get the square of the length of that projection. So this thing inside the brackets, this is the sum of the squares of the lengths of the projections of the bi on the vector u. So let's draw a little picture to illustrate what's going on. So let's say I have this data point b1, okay, and I have this vector u like this. So this vector u is going to span this line. And what I'm doing is I'm projecting b1 onto this line. So I get this, and then I take the length of this component, right? The length of this component is going to be b1 dot u. And if I have another point, maybe here, b2, then I project this vector from the origin to b2 onto the line, and I get this. I get a 90-degree angle, and I have this point, right? That's the projection of b2 on u. And this length is going to be negative b2 dot u. Right? This is the length of the projection. And I have a negative sign because b2 dot u is negative. So b1 dot u is the length of the projection of b1 onto u. And what this is, right? I have this b1 dot u here, b2 dot u there. I square them all so I get the squared lengths of the projections and I add them all up. I sum them throughout my 6 data points. Okay, and then I have this 1 over n minus 1 factor. Okay, so I can think of the variance as this 1 over n minus 1 times the sum of the lengths, sum of the squares of the lengths of the projections. Well, let's think about what happens if I take that sum b1.u squared plus dot 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 plus b6.u squared. Okay, so that's the sum of this squared plus that squared. Well, what happens if I take those and then add this squared and that squared? If I add, right, that's the distance from B1 to the line. So let's just call this the distance from B1 to the line. Let's call this line L sub u for the line along u. The distance from B1 to L sub u squared. So I take this squared plus that squared. Well, the Pythagorean theorem tells me that that's going to be this length squared, right? And similarly, if I take this squared and that squared and add them, I'm going to get this length squared. So if I take the distance from B1 to LU and then square it, and then I sum them up over my data points, so I get the distance from B6 to LU squared. If I add all these up, I just get the length of the vector B1 squared plus the length of the vector B2 squared all the way to the length of B6 squared. Right? And remember what the principal components, the first principal component does. The first principal component is the u that maximizes this. My u, which is the principal component 1, maximizes this sum. But I start out with this B1 through B6, so I'm only varying my u, right? This term is just constant. It doesn't change depending on u. So I have these 6 data points. I take the length of B1, square it, and then all the way to the length of B6 squared, okay? And then I have the sum of this purple sum and this, say this red sum. So if you're making the purple part bigger, right, if you're making this first sum bigger, you must necessarily be making the red sum smaller. This part must be getting smaller as the first sum gets bigger because the sum is constant. So what's going on is that my u, which is my principal component 1, minimizes this sum, right? It's the unit vector that's going to minimize the square of the distances from the data points to the line that's generated by the principal component. So that's what the principal component does, is it's the direction that when you project those data points onto the line spanned by that direction, okay, the distances from the data point to the line, when you square them and add them all up, that quantity gets minimized. Okay. So this principal component 1 minimizes the sum of the squared distances from the BI to the line spanned by U. That's what my principal component does. So it's sort of like least squares, right? If you have a line of best fit, okay, what that's doing, the line that you get in the least squares, is that's minimizing this vertical, it's minimizing the sum of the squares of the vertical distances. So this is from the line of best fit from least squares. You want to minimize this sum. It's this error squared plus that error squared. So if the length of this is e epsilon 1, and that's epsilon 2, you want to minimize epsilon 1 squared plus epsilon 2 squared. Now you have principal component analysis, which is where if I have these same data points, okay, I'm taking the line that minimizes the distance from the point to the line. So now I have this and this. I have 90-degree angles here. And what I'm doing is I'm minimizing that squared plus that squared, right? So if I call that one epsilon 1 and that one epsilon 2, then this is the line I get from principal component analysis. This, I have a unit length vector here. That's my principal component 1, right? It's the choice of vector that minimizes the sum epsilon 1 squared plus epsilon 2 squared, where this time I'm looking at the distance from the point to the line instead of the vertical error, right? So I can think of PCA as like orthogonal regression. Instead of least squares regression, I'm using orthogonality. So that's one way to think about principal component analysis that's not in terms of, variance, right? The first way I described the principal component is in terms of the sample variance, but this is a way to describe it that's closer to how you would describe the line of best fit in least squares. Okay? I guess the only thing left to say about this is what happens when you have a 3x3 matrix or a 4x4 matrix. We only did 2x2 matrices. And there's not that much more to say about that. I mean, basically the idea is that you, once you have the first principal component, then you take the plane that's orthogonal to U1, okay? And then the second principal component is the vector that's along that plane, that's on that plane, and that maximizes the possible variance when you only look at unit vectors on that plane. So you get orthogonal vectors U1, U2, U3, etc., all the way to UN, and those are the principal components. If I have time, I'll make another video, but this video and the previous video give you a good idea of what principal component analysis is and what it has to do with linear algebra and eigenvalues and eigenvectors. Okay, thanks.